All right, so the next speaker is Martin Savage. He'll tell us about quantum simulations using scalable circuits.
Yeah, thank you very much. I'd like to thank the organizers for putting together this wonderful meeting and inviting me to speak. I spoke to this audience in March about work that we did in January. I'm going to spend a few slides reviewing that work that leads into the new stuff, if that's okay. So I'm going to tell you mainly about what we've been doing with quantum simulations of scalable circuits. This is part of a much larger effort worldwide in doing quantum simulation. Some of the people leading these activities are in the room. I'm going to be focusing on just this narrow part. So let me show you a slide that I showed you last time, and that is August 2023 was actually quite a dramatic month for quantum simulation. So at the IBM Quantum Summit in December of that year, Jay Gambetta showed what they'd learned from what people were doing on their quantum processors. And what's shown here is the number of qubits engaged in a simulation, and here is year. And so if you remember the evolution of the hardware that was accessible, it started with 4 or 5 qubit chips around 2016, and then around this time jumped up to chips of order 100 and even a 600 processor chip. And what you see here is the jobs that were running on their systems. And there's this month, if you look at these papers, there were 7 papers that came out, all running larger than 100 qubits. And this happened in a period of, most of them happened in a period of July, August of 2023. And so what happened here was a few things. Firstly, the devices became available sometime before, and then the community figured out what to do with them. And so this is not just our community, these are all over the place. This is random quantum circuits, condensed matter materials, high energy physics, nuclear physics, and so forth. But once the devices were there, people were figuring out, well, we've been quite efficient working with 4, 5, 10, 16 qubits. Now it's time to think about how it is to go to big systems. And within a period of about 4 or 5 weeks, you saw these papers appear on the archive. So sort of an example of the problems that we want to solve is this. So this is proton-proton, high-energy scattering with highly elastic process with large high-multiplicity final states. So this is something that one will dream of asymptotically in the future of doing when one has an ideal quantum computer. We're not there yet, and we're not going to be there for a long time. And so at the moment, the community is taking baby steps towards putting in place the technology and the techniques needed to do the various elements of this type of simulation. So canonically, things fall into 3 categories. One is state preparation, one is time evolution, and then one is measurement. And so at the moment, in the state preparation side of things, we're learning how to prepare the vacuum on modest-sized systems in a scalable way. We're learning how to build wave packets. And so this is at a fairly primitive stage. I'll show you where things stand there. And at the moment, mainly we're working in 1+1D and now moving into high dimensions, but really the results that currently exist are in 1+1D. And then, of course, that includes building circuits and exploring what you can do on different types of devices. The time evolution part is also moving along nicely. One has a well-defined Hamiltonian, and we're understanding how to perform truncations and redefinitions and defining mappings to understand how one can attempt to optimally do the time evolution to take you through the collision region. The part that is not really that advanced at the moment, and it's now starting to be worked on, is the measurement part. Right? And so the thing to keep in mind there, one of the things we're thinking about doing is trying to build programmable quantum sensors or out of some of the qubits on a device and then couple them somehow to the system you're trying to simulate and then extract the relevant information from there. And the reason for that is because when at scale, you can't dump the wave function on a quantum computer to a classical computer. So you've got to be selective, just like our experimental colleagues. The pioneering papers on this were in scalar field theory that laid out the formalism from beginning to end on the S matrix. In scalar field theory, it was Jordan Lee Preskill. And I want to stress again that there's a number of groups around the world that are working towards these objectives. So the systems that we're targeting to work with, of course, are the quantum computers, but the quantum computers, in some sense, are the weak point of the computational ecosystem. One is always going to be having your quantum computer embedded in a large classical compute system, and so except for the parts of the computation that you want to do that are accelerated by a quantum computer, you're going to want to use the classical computing part of that ecosystem. So one has to think about the problem, understand how to organize it, how to figure out which parts you want to send and do on the classical computing side of things, and then which parts you want to specifically send to your quantum processor. It's very similar to when GPUs came out. You had to understand which part of the jobs you wanted to send to the GPU, and in this case, it's now what part of the jobs you want to send to the QPU. The architectures are changing relatively rapidly. For instance, we now have large cold atom systems with optical tweezers that allow you to pick out atoms from your two-dimensional array, move them into a region, entangle them, and then move them back, and so forth. One has trapped ion systems that are becoming larger, of higher fidelity, and now moving towards connecting multiple of them together. One has the superconducting qubit systems, for instance, from IBM. These are typically two-dimensional. The connectivity is improving, and also now putting together many of these processes in parallel on some quantum communication fabric. The problems and the challenges that we have is taking the physics that we want to simulate, so for instance quarks, gluons, photons, the standard model in general, and then map this onto the quantum hardware in an optimal way. And typically the hardware looks like a large number of Hilbert spaces with some connectivity between them. One has to then figure out how, for instance, you put the scalar field onto these Hilbert spaces with the efficient connectivity, or put the quarks, or put the gluons, and so forth. So this is the challenge. This is where a lot of effort in the community is going into. It's very human intensive, and it's very specialized. So if you were to hand this problem to, for instance, a computer scientist to solve this problem, you're typically not going to get the optimal solution. So the physicist, despite what the computer scientists would like to think, it's going to be the physicists that really get this problem to solution first. And of course, in collaboration. I don't want to be too obnoxious about it. Okay. So the problems that we wish to tackle is very familiar to you. For instance, in this case, we're trying to put QCD, so Yang-Mills plus quarks, onto some discretization of space-time. I've drawn here a cubic grid, but it's looking more and more like we probably won't be using cubic grids. These are effective ways to start because we understand them very well from classical computing, but it's more likely we'll be going to systems, for instance, honeycomb or trimode lattices, and I'll mention that in a little bit. The pioneering work for this, for the Hamiltonian structure, these are just some of the papers, but it spans quite a while from the creation of QCD through to some of the works of about 10 years ago. And so one has links and sites, of course. The quarks will sit on the sites, and then the gauge fields will sit on the links. And in the Hamiltonian formulation, of course, you have to put in the Gauss's law constraints by hand. And so then a lot of the detail and understanding goes into how do you actually map the gauge group onto the links. What does the Hilbert space construction look like? If you look at the connectivity, so the connectivity of U1 and SU2 is pretty similar, and in some ways they are somewhat easier to deal with and simulate. But SU3 and higher is more complicated, and so if you look at the connectivity of the group, this is where one of the new headaches comes in when trying to do SU3 and beyond. Is basically how do you move around in the gauge space? But anyway, at the end of the day, this is not anything that's unfamiliar to you. It's just latticizing a lattice gauge theory, but in this case, in a Hamiltonian framework. So one of the things that is interesting to think about is the choice of gauge. Now, normally, Nominally the choice of gauge, of course, doesn't matter. And in lattice QCD calculations in Euclidean space, you don't worry about it because under sampling, it's an exponentially small likelihood you'll end up on the same gauge orbit, so you don't worry about it. However, in the Hamiltonian simulation, it's a different story, and it turns out it makes a significant difference. And there's still there's an ongoing lot of work at the moment to figure out which gauges to actually use in going to in a higher dimension. So a couple of the gauges you like to work with in 1D, for instance, Weil gauge. So this is a gauge where you set A0 equals 0. You have a gauge field in the spatial dimension. It's completely constrained by Gauss's law, so it's not an independent degree of freedom. It's completely dictated by what's going on in the fermion field. To encode it, for instance, onto qubits, then you'd have qubits denoting the occupation of, say, the electrons and the positrons, and then you'd have a Hilbert space established through some number of qubits that accommodates the gauge field. And so this, of course, on a superconducting system means you just have to have qubits to contain the gauge field. On a trapped ion system, you can think about it like that, but the trapped ion system also has vibrational degrees of freedom, so there's recent work and suggestions indicating that you can put the bosonic degrees of freedom actually into the vibrational modes of the atoms in the trapped ion system. So you have the ions containing the occupation of the fermions, and the vibrational modes actually having the bosonic piece. But so this is in some ways Hilbert space heavy, this gauge. Now you can choose then axial gauge. So axial gauge basically means that AX equals 0, so you actually don't have registers to support the gauge field in the spatial directions. The gauge field in the temporal directions gets translated into a non-local interaction that you have to add explicitly, a charge-charge interaction between the charges, connecting all charges on the lattice. Now, it's interesting that, this one's qubit heavy, this is qubit light, but at the level of interactions and time evolution, you have this non-local interaction. It turns out when you, for instance, prepare a system and then evolve it forward in time, and you look at the total resources in this space-time volume, then both gauges, it's roughly the same. The scaling's the same, there's different coefficients, but even though it looks really quite different, the fact that this is local interactions only and this is non-local means that when you figure out what are the quantum operations, it's roughly the same. So one of the things that we did middle of last year, and I've already shown you this before, was to understand what the fact that the system 1 + 1 QED, the Schwinger model, is confining, allows you to truncate these all-to-all interactions between qubits, and so it takes the implementation of the Hamiltonian from scaling as volume squared to scaling as volume times the correlation length, or the confinement scale. And so this takes it from nominally not simulatable into the class of simulatable. So this is the Schwinger model. I should have said that first. This is the Schwinger model mapped to qubits. There's a diagonal z piece. This is the mass term. There's the hopping term, which is nearest neighbor on qubits. This is the connect term, and then this is the energy in the electric field. And this is non-local, and this is the term that adds nominally all the complexity. But confinement really saves you here. And sort of going back to one of my previous comments, this system's got a lot of symmetry. It's got discrete translational invariance. It's confining, which means the correlation lengths fall exponentially. And even with open boundary conditions, you'd prefer to use periodic boundary conditions. But even with open boundary conditions, you can still do useful things with this theory. One has edge effects that you have to worry about near boundaries, but as long as the volume part is large enough, the edge effects can actually be systematically removed. So we built upon the adapt VQE algorithm. So this was a variational quantum eigensolver algorithm developed by Sophia Economou to run on a quantum computer to basically you have your system, you have some objective function like the energy or the fidelity of the wave function, and then you have an operator pool that you randomly select from, and keep successfully built-in layers to reduce the objective function. Now, so normally running VQE on a quantum computer is sort of not a winning proposition, because the quantum computers are noisy, you get stuck in places, and it's also very time consuming. So what we did was to use the fact that because the theory is confining, you only have a localized volume of your space that you actually need to do optimizations on, and you can develop operators that with just a parameter n, if you like, or d, which then allows you to scale out, basically because of the translation invariance. So you can develop and perform simulations using classical computers in a small volume of space, and just with simple knobs and understanding physics and the exponential convergence, then change these knobs, dial them out to then produce circuits that you can then put on, say, 1,000,000 qubits if you wanted. In our case, we put them on 100 because that's what the machines available to us were, but in principle, you could go much larger. So having bounded correlation functions, exponentially falling, means that you can actually quantify the errors you're making, and you can use classical computing to stand up fairly large correlation volumes, which then you can then blow out to much larger quantum registers. So this part we do classically. There's some operator pool, and so this operator pool is now scalable operators. They're operators that have correlations between a finite number of qubits, and they can then be translationally invariant, so they can act from one side of the lattice to the other. And the other one of the things that we've learned, many things we learned from doing classical simulation, so this is lattice QCD, is the behavior of parameters as you change the volume or take the lattice spacing to 0. So in this particular instance, one has operators, and one then has corresponding quantum circuits with parameters. And in a confining system, those parameters will depend exponentially upon the volume. So as you take the volume off to infinity, these will converge exponentially to basically fixed point angles, which then can be applied in a circuit of arbitrary size. And so you can do all of this classically for pretty reasonable size volumes. And so then once you've then extrapolated these angles from doing a series of classical simulations and optimizations, you can then extrapolate to the size of the lattice that you want to apply it to. And this could be some intermediate size lattice, or it could be some very large lattice. And then the next part of this is you take this operator pool and you have to convert it to a series of unitary operators that then have to be, say, trotterized and then optimized with regard to the target function again, and then these things can apply it at scale. And so there's been a variation of this that I'll tell you about in the last couple of months that sort of generalizes a little bit. This generalizes this more. And so primarily I'm going to be showing you results obtained in these two papers with Roland Farrell, Mark Iller, and Anthony Charavella, two PhD students and a postdoc. So the types of operators here are, for the Schwinger model, are pretty simple. There's an operator that looks like the mass term. There's an operator that looks like a generalized kinetic energy term. Now, not just connecting nearest neighbor qubits, but connecting qubits that could be separated by some distance. And these are volume operators, but then there's also surface operators. This is to accommodate the fact that with open boundary conditions, you have an exponential fall-off of charges in the vacuum as you get close to the boundaries, set by the mass gap. And so there's some surface operators you introduce. And it's actually not these operators that you'll apply in the circuits, but it's the commutators of these operators, because one wants to generate a real wave function. And then the starting point of these calculations, typically you need a starting point that makes sense, and the starting point is a strong coupling vacuum. This has the correct infrared behavior, and so one can then build in local correlations without having to build in order volume types of correlations. So you start with something that has the correct behavior very far away, and then you disturb it locally. So I think I showed you this in March also. So there's some nice circuitry that was developed. A group in Europe developed some R boxes. So these are operations between pairs of qubits in terms of phase gates, Z gates, Hadamards, and rotation operators. And these R boxes have the nice the nice property that they can actually collapse and cancel each other when you put a lot of these blocks together. And so, for instance, what I've shown here is the implementation of e to the I theta xy plus or minus yx, for instance, and then including multiple z strings between them. You just concatenate these boxes, okay? And so then you can build circuits that actually compress, and then there's cancellations and so forth. And you have to then ask the question, how do you organize these circuits under trotterization? This is very nice with regard to decoherence of the machine. It's a short depth circuit, but it doesn't contain all of the correlations, or you could do this. I need to speed up a little bit. One of the things that was really helpful is decoherence renormalization. This was work done in collaboration between IBM and Berkeley. Christian sitting here. And the important part of this is that one can take the physics circuit you want to simulate, and as you're simulating, the device is turning off and becoming classical. You're losing the quantum correlations, and you can compensate this by running circuits that you know, and then by doing rescaling. Here's some results from a couple of years ago from with regard to issue 2 plaquettes, where this is the circuit, the results from the circuit measuring the decoherence. These is what comes off for the physics circuit, and then you can renormalize to recover these results. And so this led to basically factors of 10 improvement in the depths of circuits that could be simulated. So these are the results for the vacuum state. For the Schwinger model that we achieved using all of this technology on 100 qubits, these are the results that came off the device, and then after the renormalization gave rise to the points with error bars, and the dashed line is the classical expectation. So this was done on IBM Cusco. And then to build a wave packet, one can start again from the strong coupling vacuum, because you know exactly what the excitations are, do adiabatic evolution to turn on the kinetic energy term, and then recover a wave packet. Then you can use and time evolve forward to produce a beam or a pulse of hadrons, protons moving back to back on this system. And so this is the nominal circuitry. Prepare the vacuum, prepare the wave packet on top of that vacuum, some localized region of space, and then evolve forward. So these are the results that were obtained by performing that analysis. You see that you have create a wave packet here, and performing time evolution produces this light cone of back-to-back moving hadrons. This is the results from classical simulations. These are the results obtained from the quantum computer. And just here's an example of what the error mitigation strategies turns like. This is without any error mitigation whatsoever, and then this is the result after error mitigation. So you see that error mitigation is actually essential. So the recent work I want to tell you about in the last 7 minutes with regard to scalar field theory. There's been 2 works, a theoretical work coming out of Brookhaven, optimized quantum simulation algorithms for scalar field theories, and then work by my PhD student, Nikita Zemlevsky, on performing scalar field theory simulations on 120 qubits. Of course, as I mentioned, the work by Jordan Lee Preskill established all the formalism for this. So scalar field theory, one has a Hilbert space at each site that provides the digitization of the scalar field. These are then coupled together by the kinetic term, and so there's a truncation in the Hilbert space supporting the wave function of the scalar field, and then of course there's the spatial lattice of some finite dimension. So he took what we learned from using the SCADAP VQE and just wrote what the circuit structure was going to be in some bricklayer fashion, and then did variational optimization on that to prepare the vacuum state. And then to prepare the wave packet, similarly, one uses the fact that it's localized and exponentially convergent to prepare an optimization circuit, again involving entangling gates and so forth. This is a sort of a cartoon hiding a lot of circuitry here. This is a wave packet moving up, and this is a wave packet moving down. And then there's time evolution. Again, one takes a multiple trotterized evolution operator, but then you can arrive at a variational circuit that's actually much shallower than the naive application of the unitaries to actually achieve comparable precision, but with much shorter circuit depth, requiring much less mitigation. And so this is the result that he obtained from scattering scalar particles. This is on IBM FES. And so there's a scalar wave packet here and a scalar wave packet here, and goes through the collision region, it collides and comes out the other end. So this was done both with lambda equals 0 and lambda equals 2. And the thing that he was able to observe is a displacement. There was a delay through the scattering. So he's actually able to identify the fact that these wave packets, there was what you'd expect from an interaction. There's a delay in the particles emerging from the interaction region. It is small, but this is what you get with zero coupling, and this is what you get with non-zero coupling, but there's a noticeable delay. Okay, thanks. And so this was what you'd expect using matrix product simulation, and this is what was actually achieved on the quantum hardware. So, and in order to do this, he developed a different type, did an improvement on the error mitigation. He realized the fact that, if you think about what the wave function for scalar field looks like with a wave packet on it, it's very similar to the vacuum. And so he realized that the error mitigation circuit that you use for the vacuum, which you can do with much higher precision, you can also use for the wave packet. And not just for one qubit, but for also multiple correlated qubits. And so he ran through that mitigation process, and that was one of the things that made a big difference here. So this is the results, the quality that he has. I'm showing you just to demonstrate the quality of the results that you can obtain on the IBM devices when you do the mitigation, when you actually able to accomplish the mitigation as you'd like to. And so the dashed line is the results that are expected from classical simulation, and the points of the error bars are what you get from the device. Let me skip that. I want to mention one of the things we did. So now that you see that you can actually start doing these calculations and you can start increasing the energy, of course, one's appetite grows dramatically, in fact, exponentially, to trying to find a quantum advantage in these processes. But there's a lot of things that have to get put in place and a lot of systematics that have to be understood before you can possibly claim you've actually got a quantum advantage. One of those is to understand what the lattice is doing to you. And so while there's been lots of studies of lattice spacing artifacts with classical computing, in the realm of real-time dynamics, this has really not been explored much. And certainly the community of people that are working on this, we're still at the early stages of building intuition. So what do we do here? So we prepared the ground state of the Schwinger model, but with a background source. So we put in an infinitely heavy quark, in this case, positron, and then we solved for what the ground state of that was. And then we were able to actually control the location of this by changing the classical trajectory of Gauss's law. We then accelerated this up to some constant velocity, moved it across the lattice, and then slowed it down and stopped, and then asked what happened. Okay, so what happened? Well, in the region where it's moving at constant velocity, Lorentz invariance in the continuum tells you nothing's going to happen. But in fact, on a lattice, you have broken Lorentz symmetry, and you lose energy. You lose energy into the light degrees of freedom. So you start producing hadrons. And worse than that, you start really destroying the entanglement in the vacuum state. So this is the plot of the energy in the light degrees of freedom as a function of time as we pick this heavy quark up and move it across the lattice. This is when you take the differences to see what the energy the deposition is. This is the generating the EDX. And so then you ask what is the total energy loss, if you like, as a function of velocity. And while it's low, things are behaving well. And then as you go high, things you lose control quite rapidly. And what's going on is the fact that dispersion relation looks like this. This is what you have with special relativity. This is what you have with a lattice discretized action. And so as you start moving this thing really fast, you just leave behind parts of the wave function. They just can't keep up, and the thing blows up and hadronizes. I got 1 minute left to show you more stuff. So this is as different velocities. This is what happens. You see things are quite nicely well behaved. This is the charge distribution, the background charge, and then the charge in the low degrees of freedom. And as you increase the velocity, you just leave a trail of hadrons behind, which in a finite lattice just start ringing like a bell. So you've lost complete control. And if you look at the entanglement, so check out the entangles. 2 tangles, 4 tangles, up to 12 tangles that you can do, it turns out that you really destroy the entanglement structure much more dramatically than you have problems with the classical observables. So the tangles, even at velocities of 0.4, you've really destroyed what the entanglement structures look like. So one of the things here, we see here that the lattice does more violence to quantum information than it does to sort of ordinary non-quantum information. So you can do other things, and I am out of time. So you can collide partons, so you can take 2 of these things together, bring them together, the leading partons actually collide, there's information propagation through to the backside of the hadrons, which then collide less, they rearrange themselves. And you can look at the energy deposition, for instance, with a hadron-hadron scattering. You see this is what the energy deposition looks like. There's far more on the leading edge than there is on the trailing edge and so forth. Okay, so I'm out of time now. There's a whole pile of stuff I wanted to talk about. One comment, well, 2 comments. This is the state of beyond 1 dimension. This is 2 dimensions. And the most exciting thing I think Christian's going to tell you about later in the week is they'll ever use large NC to start looking at the dynamics of quite large systems in 2+1D. So this is quite an important development, and it may provide the starting point for future in higher dimensions. And there's also work now trying to use 2D honeycomb lattices. Here, this is really, I'm impressed by this work from some junior people where they looked at the evolution of the correlations of the energy momentum tensor and able to pull off something that, at least in the infinite volume limit, would go to viscosity in issue 2 gauge theory. Severely truncated, small lattice, et cetera, et cetera, et cetera. But it's on the path now to looking at transport and things. Okay, trimond lattices, different for non-cubic lattices. This is probably an important part of where things go next. Okay, I'll just leave that up. Thanks very much.
Questions?
Kind of more generic question. Say, you are in real time, right? Doing this, so it's not like being in a Euclidean domain.
Right.
The question then is, so I mean, in this way, it's not like what I would call the classical lattice theory, you know, where when you're going from this Euclidean side. But the question what I have in mind is about, let's say, it's a hadron scattering or deep inelastic, right? Then it's a question about higher twist. So when you're doing this procedure, what I am afraid that it's kind of close to perturbation theory calculation, and this higher twist contribution could be kind of out of this, and that is my question.
Yeah. So firstly, if you were to do these sorts of computations in the continuum and you had the full wave function, for instance, to arbitrary small length scales, you wouldn't have to worry about any of those things. You would just calculate the cross section.
But you're doing it in certain approximation, which is close to perturbation theory.
No. This is on the road. The idea is on the road to do an exact simulation without.
Yeah, so you can find one over Q corrections explicitly?
They would all be part of the cross section or what you measure, yeah. So all of that stuff should be in the final result. Now, of course, what you're saying is in reality is a different matter because you have a finite lattice spacing and the physics at momentum scales that are beyond, pi over a have to be put in terms of effective operators, and there's effective field theory descriptions, for instance, that Christian's been developing. But if you could take the lattice spacing to be small enough, you wouldn't have to deal with that.
I see.
But that's a long way off. So, yeah.
In the shrinker model, can you look at this phase transition for negative mass, or theta equals pi?
Yeah, so
Is something that's
I had a slide that I didn't put in, but people have been looking to address this point, quenches. So you start this and you quench theta either less than pi over 2 or larger than pi over 2, and you find a dynamical topological phase transition when you look at the 2-point correlation. So you can do this.
Other questions? Yes?
I'm just wondering how you. I think you have to modify the Jordan-Prisco for during simulation for the shear viscosity thing, right? The Jordan-Prisco is describing the in-out scattering amplitudes, but the transport coefficient those are.
Yeah, so that doesn't use Jordan
Oh,
Prisco.
it doesn't-
No, it's a totally different framework.
I see.
Yeah.
Sorry.
Yeah. Yeah.
Okay, there are no more questions. Let's